This question says, an analytical chemist weighs out 0.158 grams of an unknown monoprotic acid into a 250 milliliter volumetric flask and dilutes to the mark with distilled water. He then titrates this solution, the entire solution, with 0.1200 molar NaOH solution. When the titration reaches the equivalence point, the chemist finds that he has added 18.3 milliliters of NaOH. So in a titration, we basically look at the concentration of one reactant to tell us the concentration of another reactant. And you often use an indicator. In this case, most likely the indicator is phenolphthalein. And when it turns pink, basically you know the reaction is done. Believe it or not, if you took the lab here at UAlbany, you basically have done this reaction with citric acid, which is a tripyrotic acid. So here we are going to experimentally determine the molar mass. Generally speaking, if you want to know the molar mass of something, your first instinct is to go to a periodic table and look it up. But somebody had to calculate those things, and one way to calculate them is by titration. So let's look at how we might calculate the molar mass. Well, molar mass equals grams of acid divided by moles of acid. The grams of acid are easy. It's given in the problem. The moles of acid we need to find from this reaction. So this is a generic acid. I'm going to call it HA, aqueous. And we're going to react it with sodium hydroxide, aqueous. And when we do that, it's just like a double distillation reaction. Na goes with A and H goes with OH. And we get NaA, aqueous, plus H2O, liquid. So we form something that's not aqueous, which drives this reaction. So basically, this is our reaction. In this case, all the stoichiometry is 1:1. H goes with OH, forming one water, and that leaves us Na left over, and we get NaA. At the end of this, I'll talk about a diprotic acid, and then if they ask you about a triprotic acid, you'll have to extrapolate further. Now we need to do stoichiometry. We know the volume of NaOH that we used. We also know the concentration of the NaOH, so we can find moles of NaOH. Because this is a titration, we know that when it reaches the equivalence point, the moles of NaOH and the moles of HA are equal, so we can use the stoichiometric coefficients to determine the moles of HA, which we can then plug into our molar mass formula. Let's see how we do that. So we need to start with liters of NaOH, convert that to moles of NaOH, and then finally to moles of HA, our acid. So we have to take this and divide by 1,000, 0.0183 liters of, in this case, NaOH, times, now we need to convert it to moles. We need to use the molarity. For every 1 liter of NaOH on the bottom, so it'll cancel out, there are 0.1200 moles of NaOH. Times, we now need to use the stoichiometric coefficients in the balanced chemical equation to find out how much HA there is. Well, there's 1 mole of NaOH for every 1 mole of HA. And when you do that math, you get that this is 0.002196, and it's 3 sig figs, moles of HA. Now we know the mass of the acid, so we can plug into this formula. Molar mass equals the 0.158 grams divided by the 0.002196 moles. The molar mass to 3 significant figures, since both the grams and the moles are 3 significant figures, in this case is 71.9 grams per mole. Couple things I want to point out. First, we're told that it's a 250 milliliter volumetric flask, or said another way, we have 250 milliliters of solution. If we wanted to calculate the concentration of HA, we could. But since we titrated the entire solution, we actually don't need this number in our calculations. So sometimes we have information we don't need in problems on the book. In real life, we almost always have information that we don't actually need to solve these types of problems. The other thing I want to point out is that you may have a di or a triprotic acid in the in other problems on this test. So I just want to, or excuse me, other problems in this unit. I forgot what they call these things. So anyway, you might have a diprotic acid. So if we have a diprotic acid like H2A aqueous, and we add NaOH, the same thing is going to happen. H goes with OH, Na goes with A. However, A is going to be 2 minus now, and you're going to get Na2A aqueous plus H2O liquid. Well, we need 2 sodiums, so we have to put a 2 here. We also have now 2 OHs and 2 H's. 2 OHs and 2 H's gives us 2 waters. So the stoichiometric coefficients are going to be different. Therefore, here we would have 1 mole of HA and 2 moles of NaOH if it were a diprotic acid. If it was a triprotic acid, we would have 1 mole of HA and 3, or it would be H3A actually, and 3 moles of NaOH, and we'd make 3 water molecules. So if you get different amount of protons on the acid, you do have to change your balanced chemical equation, which will change this conversion factor.